Article 690 of the National Electrical Code addresses photovoltaic systems. Article 210.52 burn pertains to branch circuits required for receptacle outlets, stipulating that all 120 volts, 15 amps and 20 amps receptacle outlets installed in kitchens, dining rooms, family rooms, breakfast rooms, and utility rooms be supplied by separate 20 amps branch circuits. Concerning the use of number 14 NM cable for a receptacle outlet connected to a solar circuit, this can be permitted under specific National Electrical Code provisions. Article 690.8 addresses wiring methods, stating that conduit or other approved raceway shall be used for wiring between panels and controllers. Wiring from panels to modules and between modules shall be installed in accordance with 690.31 and shall be type UF sunlight resistant single conductor cable, type USM and S2 sunlight resistant multi-conductor cable, or other approved wiring methods, including factory installed wiring. Article 690.31 specifies conductors and ratings, mandating that conductors shall be coupled with a minimum insulation rating of 600 volts. Conductors smaller than number 12 AWG shall not be used. Therefore, a number 14 NM cable can meet requirements for wiring to receptacle outlets in solar circuits based on these sections. Several additional considerations apply to solar circuits. Firstly, overcurrent protection. Solar circuits should be protected by overcurrent devices rated for the ampacity of the conductors used. Secondly, grounding. All solar circuits must be properly grounded. Thirdly, labeling. Receptacles connected to solar circuits should be labeled to indicate that they are not connected to the utility grid and may not be available during a power outage. While the National Electrical Code does not explicitly address the use of solar circuits for receptacle outlets in kitchens, the provisions in Article 690 and the definition of branch circuits in Article 210 allow for the use of number 14 NM cable for this purpose, provided all other requirements are met. This includes, but is not limited to, overcurrent protection, grounding, and labeling. When installing and inspecting solar photovoltaic systems, it is vital to adhere to NEC Article 690, which provides detailed requirements for these systems. Firstly, understanding the scope of Article 690 is essential. This article covers the electrical installation of photovoltaic systems, including solar arrays, circuit conductors, inverters, and charge controllers. It aims to ensure the safe and reliable operation of these systems. Secondly, wiring methods are a critical aspect covered in Article 690. The NEC specifies approved wiring methods for connecting solar panels and other components of the system. These methods ensure that the wiring can withstand environmental conditions such as sunlight, temperature variations, and moisture. Conduit, metal-clad cable, and specialized PV wire are commonly used. Thirdly, overcurrent protection is necessary to protect the system from faults and overloads. Article 690 requires overcurrent devices, such as fuses and circuit breakers, to be properly sized and installed in the solar circuits. These devices are crucial for preventing damage to equipment and reducing the risk of fire. Fourthly, grounding is another critical safety measure. Article 690 mandates that PV systems be properly grounded to minimize the risk of electrical shock and equipment damage. Grounding ensures that fault currents can safely return to the source. Fifthly, disconnects are required to allow for the safe isolation of the PV system for maintenance and emergency purposes. Article 690 specifies the types and locations of disconnect switches that must be installed. These disconnects enable technicians to de-energize the system before working on it. Sixthly, inverters play a key role in converting the direct current electricity produced by solar panels into alternating current electricity that can be used in homes and businesses. Article 690 addresses the installation and wiring requirements for inverters, ensuring that they meet safety standards and operate efficiently. Seventhly, labeling is essential for identifying different components and circuits within the PV system. Article 690 requires specific labels to be placed on equipment such as disconnect switches, inverters, and junction boxes to provide clear information about the system's operation and safety requirements. Eighthly, rapid shutdown is a safety feature that quickly de-energizes the PV system in the event of an emergency. Article 690 outlines the requirements for rapid shutdown systems, which are designed to protect firefighters and other first responders. Ninthly, surge protection is necessary to protect the PV system from voltage spikes caused by lightning or other electrical disturbances. Article 690 recommends the use of surge protective devices to safeguard sensitive equipment from damage. Tenthly, inspections and testing are crucial for verifying that the PV system has been installed correctly and meets all applicable codes and standards. Article 690 emphasizes the importance of thorough inspections and testing to ensure the system's safety and performance. Regarding the specifics of using number 14 NM cable in solar circuits, it's important to understand the requirements for conductor sizing and ampacity. The National Electrical Code provides tables and guidelines for determining the appropriate conductor size based on the current carrying capacity and the type of insulation. Generally, number 14 AWG NM cable is rated for 15 amps, but this can vary depending on the specific installation conditions and the derating factors that apply. In solar circuits, conductor sizing is particularly important due to the potential for high temperatures and continuous operation at maximum power. The NEC requires that conductors be derated for ambient temperature and the number of current-carrying conductors in a raceway or cable. This derating ensures that the conductors do not overheat and cause a fire hazard. The use of number 14 NM cable in a solar circuit may be acceptable if the calculated ampacity of the circuit is less than or equal to the ampacity of the cable after derating. However, it's important to carefully consider all applicable derating factors and to consult the NEC tables to ensure compliance. It is also essential to verify that the overcurrent protection device is properly sized to protect the number 14 NM cable. The overcurrent device should have a trip rating that is equal to or less than the ampacity of the cable after derating. In addition to conductor sizing and overcurrent protection, it is crucial to consider the voltage drop in solar circuits. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the solar system. The NEC recommends limiting voltage drop to a certain percentage of the source voltage. To minimize voltage drop, it may be necessary to use larger conductors or to reduce the length of the circuit. Another important consideration for solar circuits is the use of appropriate wiring methods. The NEC specifies approved wiring methods for different types of installations, including solar systems. These wiring methods are designed to protect the conductors from physical damage, moisture, and other environmental factors. Common wiring methods for solar circuits include conduit, metal-clad cable, and specialized PV wire. Each wiring method has its own advantages and disadvantages, and the choice of wiring method will depend on the specific installation conditions. In summary, the use of number 14 NM cable in solar circuits is a complex issue that requires careful consideration of several factors, including conductor sizing, ampacity, overcurrent protection, voltage drop, and wiring methods. It is essential to consult the NEC and to work with a qualified electrician to ensure that the installation complies with all applicable codes and standards. Additionally, labeling requirements for solar circuits are very important. The NEC requires that all components of the solar system be clearly labeled to identify their function and voltage. This labeling helps to prevent confusion and ensures that the system can be safely operated and maintained. Labels should be durable and resistant to fading, and they should be placed in a location where they are easily visible. Some specific labeling requirements for solar circuits include identifying the system voltage, the maximum current, and the location of disconnect switches. It is also important to label any equipment that is connected to the solar system, such as inverters and charge controllers. Proper labeling is essential for the safety of workers and for the proper operation of the solar system. Furthermore, rapid shutdown requirements are a critical safety feature for solar PV systems. Rapid shutdown allows first responders to quickly de-energize the PV system in the event of an emergency, such as a fire. This reduces the risk of electrical shock and allows firefighters to safely access the building. The NEC specifies the requirements for rapid shutdown systems, including the location of the shutdown switch and the time it takes to de-energize the system. Rapid shutdown systems typically use a combination of disconnect switches and electronic controls to quickly shut down the PV system. The shutdown switch must be readily accessible to first responders, and it must be clearly labeled to indicate its function. It is important to test the rapid shutdown system regularly to ensure that it is functioning properly. Regular testing helps to identify any potential problems and ensures that the system will operate as intended in an emergency. In conclusion, solar circuits require careful attention to detail and adherence to the NEC to ensure safety and performance. From conductor sizing and overcurrent protection to labeling and rapid shutdown, there are many important considerations to keep in mind. Working with a qualified electrician and consulting the NEC are essential steps in the process. Remember, the information provided here is for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician and refer to the latest edition of the NEC before undertaking any electrical work. The use of specific conductor sizes like number 14 AWG-NM cable in solar circuits necessitates a detailed understanding of ampacity, dirtying factors, and applicable NEC regulations. Ampacity refers to the current carrying capacity of a conductor, which is the maximum amount of current a conductor can safely carry without exceeding its temperature rating. The ampacity of a conductor depends on its size, material, insulation type, and installation conditions. Number 14 AWG-NM cable, commonly used in residential wiring, typically has an ampacity of 15 amps under normal conditions. However, various dirtying factors can reduce this ampacity. Dirtying factors are adjustments applied to the ampacity of a conductor to account for conditions that can affect its ability to dissipate heat. These conditions include ambient temperature, the number of current-carrying conductors in a raceway or cable, and the presence of insulation or other materials that can restrict heat flow. The NEC provides tables and guidelines for determining the appropriate dirtying factors for different installation conditions. For example, if number 14 AWG-NM cable is installed in an area with a high ambient temperature, the ampacity must be derated to account for the increased heat. Similarly, if multiple current-carrying conductors are bundled together in a cable or raceway, the ampacity of each conductor must be derated to prevent overheating. In solar circuits, dirtying factors are particularly important due to the potential for high temperatures and continuous operation at maximum power. Solar panels can generate significant amounts of heat, which can affect the ampacity of the conductors. Additionally, solar circuits are often exposed to direct sunlight, which can further increase the temperature of the conductors. Therefore, it is crucial to carefully consider all applicable dirtying factors when sizing conductors for solar circuits. To ensure compliance with the NEC, it is essential to consult the relevant tables and guidelines for determining ampacity and dirtying factors. These tables provide detailed information on the ampacity of different conductor sizes and insulation types, as well as the dirtying factors for various installation conditions. The NEC also includes specific requirements for conductor sizing in solar circuits which must be followed to ensure safety and reliability. In addition to ampacity and dirtying factors, it is also important to consider the voltage drop in solar circuits. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the solar system. The NEC recommends limiting voltage drop to a certain percentage of the source voltage. To minimize voltage drop, it may be necessary to use larger conductors or to reduce the length of the circuit. In summary, the use of number 14 AWG-NM cable in solar circuits requires careful consideration of ampacity, dirtying factors, voltage drop, and applicable NEC regulations. It is essential to consult the NEC and to work with a qualified electrician to ensure that the installation complies with all codes and standards. Moving on to overcurrent protection, this is a critical aspect of electrical safety in all circuits, including solar photovoltaic systems. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect conductors and equipment from damage caused by excessive current flow. Overcurrent can occur due to various factors, including short circuits, ground faults, and overloads. Short circuits occur when there is a direct connection between two conductors with different voltage potentials. This can result in a very high current flow, which can quickly damage conductors and equipment. Ground faults occur when a conductor comes into contact with a grounded surface, such as a metal enclosure. This can also result in a high current flow, which can pose a shock hazard to people who come into contact with the grounded surface. Overloads occur when a circuit is subjected to a current flow that exceeds its rated capacity. This can happen when too many devices are connected to the circuit or when a device draws more current than it is designed for. Overcurrent protection devices are designed to interrupt the flow of current when it exceeds a certain level. Fuses are one type of overcurrent protection device. A fuse consists of a thin strip of metal that melts and breaks the circuit when the current exceeds the fuse's rating. Circuit breakers are another type of overcurrent protection device. A circuit breaker uses a mechanical mechanism to trip and interrupt the circuit when the current exceeds the breaker's rating. Both fuses and circuit breakers are designed to protect conductors and equipment from damage caused by overcurrent. However, they have different characteristics and are suitable for different applications. Fuses are typically less expensive than circuit breakers and are often used in applications where cost is a major concern. Circuit breakers are more convenient to use than fuses, as they can be reset after they trip. They are also more accurate than fuses and can provide better protection against overcurrent. The NEC provides detailed requirements for overcurrent protection in all types of electrical circuits, including solar photovoltaic systems. These requirements specify the types of overcurrent protection devices that must be used, their ratings, and their locations in the circuit. In solar photovoltaic systems, overcurrent protection is particularly important due to the potential for high current flow from the solar panels. Solar panels can generate significant amounts of current, especially under sunny conditions. This current can damage conductors and equipment if it is not properly controlled. The NEC requires that solar or photovoltaic systems be protected by overcurrent devices that are sized to protect the conductors and equipment from the maximum current that the solar panels can generate. The overcurrent devices must also be located in a readily accessible location so that they can be easily inspected and maintained. In addition to overcurrent protection, solar photovoltaic systems must also be properly grounded to protect against electrical shock hazards. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and interrupt the flow of current. The NEC specifies the requirements for grounding solar photovoltaic systems, including the size and type of grounding conductors that must be used. In summary, overcurrent protection and grounding are critical aspects of electrical safety in solar photovoltaic systems. These measures help to protect conductors and equipment from damage caused by overcurrent and to protect people from electrical shock hazards. It is essential to consult the NEC and to work with a qualified electrician to ensure that solar photovoltaic systems are properly protected. Now let's talk about grounding requirements for solar circuits. Grounding is a crucial safety measure in electrical systems, including solar photovoltaic systems. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip overcurrent protection devices and interrupt the flow of current. This reduces the risk of electrical shock and equipment damage. The NEC specifies the requirements for grounding electrical systems, including solar photovoltaic systems. These requirements are designed to ensure that the grounding system is effective in protecting people and equipment from electrical hazards. There are two main types of grounding systems used in electrical systems: equipment grounding and system grounding. Equipment grounding is the connection of non-current carrying metal parts of equipment to ground. This includes metal enclosures, raceways, and other metal parts that could become energized in the event of a fault. Equipment grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and interrupt the flow of current. System grounding is the connection of one of the current carrying conductors of the electrical system to ground. This is typically the neutral conductor in a 120V/240V system or the grounded conductor in a direct current system. System grounding helps to stabilize the voltage of the electrical system and to provide a reference point for measuring voltage. In solar photovoltaic systems, both equipment grounding and system grounding are required. Equipment grounding is required for all non-current carrying metal parts of the solar photovoltaic system, including the solar panels, the mounting structure, and the inverters. System grounding is required for the direct current side of the solar photovoltaic system. The grounding conductor must be sized according to the NEC and must be connected to a grounding electrode system. A grounding electrode system typically consists of one or more ground rods or ground plates that are buried in the earth. The grounding electrode system provides a low impedance path to ground, which helps to ensure that fault current can flow back to the source. In addition to the grounding electrode system, the grounding conductor must also be bonded to any nearby metallic water pipes or gas pipes. This helps to create a common ground potential and to reduce the risk of electrical shock. The NEC also specifies the requirements for grounding the alternating current side of the solar photovoltaic system. The alternating current side of the system must be grounded according to the requirements for other alternating current electrical systems. It is important to note that the grounding requirements for solar photovoltaic systems can be complex and may vary depending on the specific installation. It is essential to consult the NEC and to work with a qualified electrician to ensure that the solar photovoltaic system is properly grounded. Finally, let's cover labeling requirements for receptacles connected to solar circuits. Labeling is an essential part of ensuring the safety and proper operation of electrical systems, including those powered by solar circuits. Clear and accurate labeling helps to identify the purpose and characteristics of different components, reducing the risk of confusion and potential hazards. For receptacles connected to solar circuits, specific labeling requirements exist to inform users that these outlets are powered by a source other than the traditional utility grid. This is particularly important because solar circuits may have different voltage characteristics or may not be available during a power outage. The National Electrical Code provides guidelines for labeling electrical equipment, including receptacles. These guidelines typically require that labels be durable, legible, and permanently affixed to the equipment. The labels should clearly indicate the voltage and current ratings of the receptacle, as well as any other relevant information. In the case of receptacles connected to solar circuits, the label should also indicate that the power source is solar and that the receptacle may not be available during a power outage. This information can help users to avoid overloading the circuit or using the receptacle during a power outage when it may not be functional. There are several ways to label receptacles connected to solar circuits. One common method is to use a pre-printed label that specifically identifies the receptacle as being powered by solar energy. These labels are typically available from electrical supply stores and can be easily applied to the receptacle. Another method is to use a label maker to create custom labels. This allows for more flexibility in the design and content of the label. However, it is important to ensure that the labels are durable and legible. In addition to labeling the receptacle itself, it may also be necessary to label the circuit breaker or fuse that supplies power to the receptacle. This helps to identify the circuit as being powered by solar energy and can prevent accidental disconnection of the circuit. The labels on the circuit breaker or fuse should be clear and easy to read. In summary, labeling is a critical aspect of ensuring the safety and proper operation of receptacles connected to solar circuits. The label should clearly indicate that the power source is solar and that the receptacle may not be available during a power outage. This information can help users to avoid overloading the circuit or using the receptacle during a power outage when it may not be functional. It is essential to consult the NEC and to work with a qualified electrician to ensure that receptacles connected to solar circuits are properly labeled. The NEC provides a comprehensive set of standards and guidelines for electrical installations, including those involving solar photovoltaic systems. These standards are designed to ensure the safety and reliability of electrical systems and to protect people and property from electrical hazards. The NEC is updated every 3 years to reflect the latest advances in technology and to address emerging safety concerns. It is essential for electricians, installers, and inspectors to stay up to date on the latest edition of the NEC to ensure that their work complies with the current standards. The NEC covers a wide range of topics related to electrical installations, including wiring methods, overcurrent protection, grounding, and equipment labeling. It also includes specific requirements for solar photovoltaic systems such as conductor sizing, overcurrent protection, and disconnects. The NEC is a complex and detailed document, and it can be challenging to navigate. However, there are many resources available to help people understand and comply with the NEC. These resources include training courses, seminars, and online forums. It is also helpful to consult with a qualified electrician who is familiar with the NEC. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations in a particular area. It is important to check with the local authorities to determine what codes and regulations are in effect. Compliance with the NEC and other applicable codes and regulations is essential for ensuring the safety and reliability of electrical systems. Failure to comply with these standards can result in fines, penalties, and even criminal charges. It can also increase the risk of electrical shock, fire, and other hazards. In conclusion, the NEC is a critical resource for ensuring the safety and reliability of electrical installations, including those involving solar photovoltaic systems. It is essential to stay up to date on the latest edition of the NEC and to consult with a qualified electrician to ensure that your work complies with the current standards. Remember that electrical work can be dangerous, and it is always best to err on the side of caution. If you are not comfortable performing a particular electrical task, it is best to hire a qualified electrician to do the work for you.